I welcome all of you to the class of chemistry, and uh, let us revise what we have studied yesterday. Yesterday we have studied about the distribution of energy for the various gases. So to understand the distribution of gases, because in gases there are a good amount of or a huge number of molecules or particles available. They are in continuous motion, but their motion is not with the same speed. So to understand, we plot a graph of we plot a we plot a graph for number of molecules versus speeds, and in this graph we can easily see that there are two graphs. These two graphs represents two different temperatures, and at various temperatures we have got two different graphs. Now, instead of studying the speed of each and every particle, we determine to study speed. So we take an average of the speed. So we take we sum the speed of all the particles divided by the number of particle, and we get the average speed. Apart from that, we even study two different other speeds. First speed that we study is known as the most probable speed, UMP, and we even study the root mean square speed, which is known as the URMS. You can see that for both the temperature T1 and T2, the value of UMP, UAV, and URMS are different. Here at temperature T2, even you can see in this graph that the values are absolutely different. And that is why, my dear students, we can see, we study them separately, all these three speeds. The value of root mean square speed is the highest. You can see that from here itself, you can easily understand that the value for root mean square speed is the highest, whereas the value of most probable speed is the lowest. But you can see that the number of molecules that have the most probable speed, their number is very much. Then it comes to the average speed, and then it comes to the root mean speed. So the number of molecules that possess the root mean square speed is the lowest among all these three, whereas the number of molecules that possess most probable speed is the highest number, or maximum number of molecules possess the most probable speed. This is how, my dear students, we have studied about the speeds of these gases. The speed of gas generally depend upon two factors. First is temperature, that we have seen that when the temperature is increased, the URMS speed or the UMP, most probable speed or average speed increases. So when the temperature increases, the speed increases, my dear students. At the same time, you can even see that when the mass increases, speed decreases. So here we have the graph for the mass for two different elements. One is for chlorine and another is for nitrogen. So when you look at the molecular speed, you can see that the molecular speed, most probable speed for chlorine is less than the most probable speed for nitrogen. And this is how we can easily understand that as the mass increases, the most probable speed decreases. Even in the previous graph, you can see that as the temperature increases, the top of the graph, or you can see that the graph little bit flattens from the surface, and this is how we understand the changes into the temperature as well as the changes into the mass. The meaning of broadening of curve shows that number of molecules moving at higher speed increases. So when you increase the temperature, the number of particles moving with the higher speed even increases. And when we compare this three types of velocities or speeds. RMS speed is more than the average speed, and average speed is more than the most probable speed. And if we take the ratio of UMP is to UAV is to URMS, it is 1 is to 1.128 is to 1.224. So please learn these definitions and these ratios, and I hope you understood it well yesterday. Now we should start today's class, and let's start studying about the van der Waals corrections and the real gas equation. So we have seen that there were two incorrect or improper um, postulates into the kinetic molecular theory of gases. Now what happens, my dear students? First, we need to study about the correction of which was done by the van der Waals. So first we shall study about the pressure correction. So let's have a look to the pressure correction. Real gases deviate from ideal behavior because the assumption there is no force of attraction between the molecules or particles of gases is not true. At low pressure, the forces of attraction are very small in value, but at higher pressure they are effective. So, my dear students, the particles attract each other, and definitely at low pressure they can be seen very easily. But even higher pressure, at higher pressure they exist, but they are not effective. These force of attraction effective at high pressure and do not allow molecules or particles of gases to collide with their full impact with the wall of the container as well as with each other. So when these particles are going to collide with the wall of the container, they are attracted back. They are attracted. Suppose one particle is going to collide with the wall of the container, then the other particles attracts that particles, and the particle does not go and collide with the wall of the container with its full effect. Some effect is being decreased due to the presence of the uh, interparticle attraction or intermolecular attraction. Because attractive forces among the gaseous molecules or particles drag these molecules back with the when they collide with the wall of the container, and thus they do not collide with the wall of the container with full impact. Thus, pressure exerted by real gases is somewhat less than the pressure calculated for the ideal gases. This is very important topic or point to remember, that whatever the pressure that we have studied about the real gases and that that we have observed about the real gases and that we have calculated about the ideal gas, you can see here that we have pressure and volume. So you can see that the pressure differs for the real gas and ideal gas. Here even you can see that the pressure differs for the real and ideal gas. At some point of pressure and volume they are same, but for most of the pressures and volume they are different. It means that the pressure of the real gas and pressure of the ideal gas are not the same. If they were same, we would not have got two different curves, but we would have got the same curve, or these both curves should coincide. The pressure exerted by real gas is somewhat less than the pressure calculated for the ideal gas. Thus, real gas exerts less pressure than the ideal gas. Please remember that the real gas exerts less pressure than the ideal gas. The less pressure exerted by real gas as compared to the ideal gas is expressed by the following equation. So now uh, the difference between the pressure of ideal gas and pressure of real gas, we can write it this way. Ideal gas exert more pressure than the real gas. So the pressure exerted by ideal gas minus pressure exerted by real gas is represented with the formula, or is written in the form of formula as if P ideal minus P real is equal to P ideal minus P real is equal to AN square upon V square. Now this is what it was determined by the scientist named van der Waals, and that is why van der Waals made the correction. As van der Waals observed that the ideal gas do not behave exactly like the real gas, this correction is made by the van der Waals, and this formula an square upon v square is even determined by the scientist van der Waals. So let us understand each terms, the meaning of each terms here in the formula. Here P ideal is the pressure exerted by pressure calculated or pressure exerted by ideal gas. P real is the pressure measured for the real gas. A is known as the van der Waals constant. N is the moles of the gases, and V is the volume of the gas. So this is how, my dear students, we can write the next equation, and therefore we can write P ideal is equal to P real plus A n square upon V square. See, this equation PV is equal to nRT is called ideal gas equation. In this ideal gas equation, this P is P ideal. Actually, in this equation, this P represents the P ideal. And this P has to be replaced with this when we write the real gas equation. Now, my dear students, we are going to study about the volume correction. This V actually represents the V ideal. This V represents the V ideal. So we may correct the V even. Now let us move forward and understand the volume correction, my dear students. You know, there are two types of forces. One is attractive forces, another is the repulsive forces. So repulsive forces comes into play when molecules or particles comes very closer. So when these particles come closer, the repulsive forces come into play, they start acting. Thus, at high pressure, particles come closer and impenetrable. Behave like a impenetrable means that cannot be penetrated or that cannot be passed through, or you can say that cannot be entered in. So what happens, my dear students, that these particles at high pressure, they have the repulsive force starts, and to a certain distance, they cannot come closer because the repulsive forces comes into play, and this is how the repulsive forces exist, and the molecules of gases, they do not come closer to great extent, or they cannot enter into one another. So they behave like the impenetrable spheres, and due to the repulsive forces, they maintain certain distance. So now, my dear students, if you have this volume V, and if you apply pressure, then when you apply the pressure, my dear students, you make these particles to come closer, 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 and at maximum pressure, these particles, they may come closer and they have only this small volume. So all these particles make a very small volume like this. But my dear students, this small volume is not negligible. You cannot neglect this volume because it is the volume. Though in comparison to this, it is small, but it's still there. And they acquire some volume, or the gaseous particles, they acquire some volume. This volume is known as B. So the empty space is not actually so big, but still the empty space is V minus B. So this is the space that a gaseous particles get when it is moving freely into V volume. Remember, my dear students, what I am suggesting is, suppose I have a gaseous particle, this. So this gaseous particle will will not have V volume to move, but this particle will always have V minus B volume to move. So this particle can move into the V minus B volume, not into completely V volume. This is what the Van der Waals tried to explain us. So if now let's have look through this. So you can see that we have V volume for 1 mole of gas. Now, if we apply the pressure at maximum pressure, the volume of the various particle become B. So for each particle, we have V minus B volume free for their movement. So blue shaded region is representing V minus B for 1 mole, that is per mole, whereas green dots, this green dots represents the B volume per mole. For 1 mole of gaseous particles, we have the volume B. So if all particles or molecules present in 1 mole of gas by increasing the pressure are brought minimum closure, they occupy the volume V per mole. That's what I just said to you. So they occupy some minimum. So when 1 mole of gas particle are added to container of volume V, for any particle to occupy maximum volume is actually volume V minus B. Remember, if a gaseous particle is entered into the space V or volume V, actually for gas to move or to occupy, only V minus B volume is available, because B volume is because of the volume of the gaseous particles, and therefore because B is the volume of 1 mole of gas particles, and therefore for real gas, my dear students, for real gas, V real is equal to V minus B per mole. So for 1 mole of gas, if there is V volume, then V real is equal to V ideal minus B. So V real is equal to V ideal minus B, or for N mole if we want to write, we can write V minus NB, and that is why, my dear students, the value V into the here B is called, please remember that B is called the Van der Waals constant, which is a volume correction constant. B is the minimum volume that gas particles occupy per mole. So now, my dear students, we had a ideal gas equation. So here we have ideal gas equation. For P, we write P plus AN square upon V square. For V, my dear students, we write V minus NB. And finally, we get P plus AN square upon V square. V minus NB is equal to nRT. And this equation is called the Van der Waals equation, or the real gas equation. So this equation is obtained for the real gas, and that is why it is called real gas equation. For 1 mole of the gases, now the same equation, if you want to write it for 1 mole, you know that this end represents the moles, this end represents the mole, and this end represents the mole. So if we substitute 1 here, we will get the real gas equation or Van der Waals equation for 1 mole. And for 1 mole, my dear students, we write P plus A upon V square. V minus B is equal to RT, because all N can be replaced with 1. And this is the equation. This is the real gas equation for 1 mole of van der Waals gas is called the van der Waals equation for real gas for 1 mole. So this is how, my dear students, we study about the correction done by the van der Waals. Now if you have any doubt, you can ask me. I wish you can reply faster. अगर आपको समझ में नहीं आ रहा तो तुरंत पूछ लीजिए या ये बता दीजिए कि आपको समझ में आ गया है.
Yes, sir.
समझ में आ गया है?
Yes, sir.
Yes, sir.
Okay, चलिए then let's move to the next point,
Yes,
which
sir.
is known as the significance of the van der Waals constant. Now let us try to study the significance of the van der Waals constant, and let us move to it. Van der Waals constant A. First, we shall study about the van der Waals constant A. Van der Waals constant A represents the magnitude of intermolecular forces of attraction among the molecules or particles of gases. So actually A represents the intermolecular forces of attraction. More is the value of A, more is the intermolecular forces of attraction. So if you have more value of A, more will be intermolecular force of attraction. Gases with more value of A can be easily liquefied. Remember, for those gases which have the value of A is more, these gases can be easily liquefied. So these are the points of significance for A, how A affects the various characteristics. That is what we can understand. Now, my dear students, here we are going to study about the units of A. So you can see that P ideal plus P real plus some pressure. So P ideal is equal to P real plus AN square upon V square. Therefore, AN square upon V square is equal to pressure, that is P. We know that pressure is equal to force per area, and therefore AN square upon V square represents pressure, or AN square upon V square is equal to force per area. Therefore A is equal to, now if we take this only A this side, so V goes and multiply with P and N square comes into the denominator. So we get A is equal to PV square upon N square. That is A force into V square divided by N square into area. Now let us put the various units for this, my dear students. So when we put the various units, we can see that the force, so for force we write this Newton, for volume we write meter cube and then we take square, then for moles we write mole, that is square, and for area we write meter square. Ultimately we get Newton into meter to the power 6 divided by meter square into mole square, and then by doing the subtraction of the powers, we can get Newton into the meter to the power 4 per mole square. So we have two different units. First unit is here this liter. Now let us look at the one more unit that we need to study about. If we look at the pressure, my dear students, then we can find that pressure is represented into atmosphere, volume is represented into liter square, and mole square is represented as mole to the power minus 2. So the another unit we can have is atmosphere into liter square per mole square. So A can have these two units, liter into atmosphere per mole, Newton into meter to the power 4 mole. Now instead of atmosphere, if we use the unit bar, then the next unit will be liter square bar per mole to the power minus 2, and we may have liter square Pascal mole to the power minus 2. Value of A, please remember, this is even very important point for you to remember, that value of A is independent of temperature and pressure. The value of A, that is, does not depend upon the temperature and pressure. Now, my dear students, one more important point for you, that gas helium has got the smallest value of A, Gas helium, please remember, gas helium has got the smallest value of A and it is difficult to liquefy. Now, my dear students, we want to study about the van der Waals constant B or the significance of van der Waals constant B. Van der Waals constant B represents total volume occupied by 1 mole of particles of gases, that is particle, maybe atom, molecule, ion, whatever present in the gas at that particular time when we study it. B is also called the excluded volume or co-volume. Please remember, my dear students, if you hear the word excluded volume or, or if you hear the word co-volume, both these words represents B. Now let us study about the units of B. So you know we are well aware that V ideal is equal to V minus NB and therefore NB is equal to volume and therefore B is equal to volume per mole. Therefore units L per mole, you can easily see that B is equal to volume per mole. Volume if you write in liter, then it is liter per mole. Volume if you write into the meter cube, then it is meter cube per mole. Or volume per mole, you can generally write it this way. And this is how, my dear students, we understand the various units of your um, B, that is what it is, the significance of the van der Waals constant B. Smaller the value of B, better is the liquefaction of gases. Remember that smaller is the volume of B, better would be the liquefaction of gases. So for gases to be liquefied very easily or very comfortably, the value of A must be higher and the value of B should be smaller. So when a gas has small value of B and big value of A, the gases or that particular gas can be easily liquefied. Now, my dear students, I am going to, or we are going to discuss one question with you. Write a short note on compressibility factor. So here we are going to understand a very important point which is known as the compressibility factor. Dear students, this compressibility factor is very important to understand and let us understand it in detail. Compressibility factor of a gas is the ratio of actual molar volume of the gas to the molar volume of a gas if it were an ideal gas at temperature and pressure. Now, I think I need to understand it, I need to make you understand it well. Compressibility factor of a gas is the ratio of actual molar volume of the gas is to the molar volume of a gas if it were an ideal gas. So suppose I take nitrogen gas and this nitrogen gas when I measure its volume, that is V, that I call it V real. Now at some condition, let's say nitrogen gas behave like an ideal gas and I make it and at that time I measure its volume, it is represented as V or the new volume that I get for nitrogen when it is real is V dash real. So here the compressibility factor which is denoted by Z, this Z is equal to V real divided by V ideal. That is what it says. Compressibility factor of a gas is the ratio of actual molar volume. Sorry, I made a mistake. Yeah, it's right. V real by V ideal. Actual molar volume of the gas to the molar volume of the gas. If it were an ideal gas, it is represented by Z. The deviation from ideal behavior can be measured in terms of compressibility factor. So whenever we want to measure the deviation from ideal behavior, we can measure it in the form of Z, which is known as the compressibility factor. Compressibility factor Z is also the ratio of product. Compressibility factor of Z is also the ratio of product PV and nRT. So you know we write PV is equal to nRT If the gas is real, you will find that 1 is equal to PV upon nRT. So here you can easily understand that when the value of Z is equal to 1, the gas is ideal. But if the value of Z is not equal to 1, then the gas is real gas and it shows deviation from the ideal behavior. So remember that if the value of Z, compressibility factor, is not 1, then the gas is the real gas and it deviates from the behavior of the ideal gas. So let's see, for a ideal gas, my dear students, for ideal gas, Z is equal to 1 for all temperatures and pressure, because for ideal gas, PV is equal to nRT and PV by nRT is equal to 1. When Z is greater than 1, it is called positive deviation, and when the value of Z is less than 1, it is called negative deviation. So even the deviation from the um, even the deviation from the ideal behavior are of two types, positive deviation and negative deviation. So I hope, my dear students, you have enjoyed today's class. Let us do a small revision about the things that we have studied in today's class. We have seen that the van der Waals equation, or we have seen that van der Waals has made some correction. So these corrections are are about the two incorrect postulates. The first postulate, that there was no force of attraction between the particles of gases, but yes, there was force of attraction between the particles of gases, and that is why the ideal gas exerts more pressure as compared to the real gas, and that is why the pressure exerted by the real gas is equal to the pressure exerted by ideal gas minus an square upon v square, and that is what we have the correction. Same way, my dear students, the volume of the gaseous particle is not actually negligible. It is there, and the volume for 1 mole of particle is represented as B, and that is how uh, the volume is represented as B. And for 1 mole, we can write the volume available for the any gaseous particles to move into V volume is V minus B. So if we have n mole, then it is going to be V minus NB.